remember Dave was talking about what he called the long path, where he communicated to the island. So the short path, he couldn't establish communication, and so he went the long path, which is pointing the antenna the opposite way and going all the way around the world by bouncing multiple times off the ionosphere and the ground. But each hop is about 4,000 kilometers. Lots of questions on the exam around hops and multiple hops and how long the distances are and what frequencies and so on. All right, so we've got the basic idea of different types of propagation. We now need to look at the way these hops work at high frequency and understand the ionosphere, which is the cause of the hops. Okay, so we've got we know that we've got this layer around the Earth which protects us. We've got the ozone layer, and you know that if it wasn't for the ozone layer, we'd all get burnt to a crisp with the ultraviolet light from the sun. So the outer layer of the Earth's atmosphere is absorbing that ultraviolet light, and ultraviolet is very high energy. Remember, on that scale, we go from low frequency to high frequency. So it is very high frequency. It's beyond radio, heat, light. It's high energy, and the effect of that is the light, when it hits the ionosphere, it causes the atoms to ionize. So ionize means the electron jumps out of the atom and becomes separated. And this is occurring at really high altitudes. So jets fly about 40,000 feet. That's really low down. So this is sort of down in the troposphere here, which is where we live. Above that, there are other layers. We're not too interested in the layers, but the ionosphere is right up here at about 300 kilometers above the Earth. So at that level, as you get higher and higher, the gases get thinner and thinner, and out here the gas is really thin, and it's being exposed to the sun, and that includes the X-rays, the gamma rays, the ultraviolet, all of that energy coming from the sun. And as a result, it's becoming ionized. Also, as the gases get out here, the gases separate, so we get, I'm not sure what all the gases are, but you've got oxygen separating out from, what else have we got in there, nitrogen. So you've got, what's happening is different layers are forming with those different gases, also exposed to different radiation from the sun, whether it's X-rays or ultraviolet. All right, so we've got a picture here, and so out here we've got, we're out here in the ionosphere, and we've got, so all of this represents the ionosphere, and we define this by these different layers, which have effects on radio propagation. So these are letters D, E, and F as the layers. So here we've got the D layer is the one closest to the Earth, the E layer is above it, and the outer region is the F layer. And then during the daytime, that F layer splits into two layers, which we call F1 and F2. So I'm not sure there's much to say about that. But these layers have different effects. So I've got some notes here. The D layer on the causes. The D layer is nitric oxide being exposed to X-rays. The F layer is oxygen being exposed to ultraviolet. And that's what's causing this separation of these layers. All right, another view of that. So we've got the inner one, the D layer, E layer, and then at night time we've got a single F layer, and during the daytime we've got the two F layers. So what's happening here is at night time the ionosphere is in the shadow of the Earth. It's not receiving any radiation from the sun, and so we've got, I guess, some leftover ionization that is maintaining this F layer. As this Earth spins and that layer comes into the daylight, it starts exposing the F layer, causing a split, but the energy is then getting through the F layer to the sun and forming an E layer and a D layer during the daytime. And the amount of ionization depends on how much exposure we've got to the sun. So just as the hottest part of the day is around noon or early afternoon, that is the time of peak ionization that we get in the ionosphere. Okay, lots of questions on this on the exam. Okay, so the reflection that we get when we send up a radio wave at HF, high frequency, it tends to pass through the D layer and the E layer and bounce off the F layer, and that gives us that long distance communication. So that's where we get the 4,000 kilometer skip. Right, so again some definitions here of what happens with those layers. I didn't talk about the E layer and the F layer. So the F layer is the one which gives us the greatest long distance skip. We can get skip off the E layer, usually at a higher frequency. So around 50 megahertz, you might get an E layer. Or there are times under very high radiation from the sun where we can form E layers. It's called sporadic E because it doesn't stay there all the time, but it happens sporadically. So we may get some reflection off the E layer. The D layer, the only thing the D layer does is absorb the radio wave and stop it getting through to the E layer or the F layer. So during the daytime, let's go back to that slide. At lower frequencies, during the daytime, the radio waves will not be able to penetrate that D layer. Where at night, when the D layer collapses, those lower frequency radio waves will get through, and you'll get some skip off the F layer. So the demonstration of this really is, if you ever listen to AM radio, you'll notice during the daytime you can hear all the local stations because that's all you can receive because you've got no skip happening. At night time, that D layer collapses and you can get longer distance stations. So you can start hearing stations down in the middle of the US because they're now skipping off the F layer and not being absorbed by the D layer. Okay, so generally the effects are the high frequency, we get skip off the F layer. We can get that during the day time. We can have the okay. So where am I going with this? So during the day, we get more ionization, and we can get skip at higher frequencies off the F layer. At night time, there's less ionization. We still have an F layer, but we can only use the lower frequencies during the daytime. The E layer, we can get skip off the E layer, usually at high frequencies. and the D layer is just an absorbing layer, which during the daytime absorbs the lower frequencies, but will let through the higher frequencies. All of this depends on how much radiation is coming from the sun, and we're going to look at how the sun behaves and how the sun changes over time. But there are times when the sun becomes really active and we get these things called ionospheric storms, where it's being exposed to higher levels of radiation. It could be UV, it could be X-ray, and we also get particles being emitted by the sun that get trapped in the ionosphere. So that's the effect we call the aurora, where the particles are penetrating the ionosphere and glowing. So when we get intense levels of radiation, we can get these things called ionospheric storms. And that can have a pretty devastating effect on communication. Under a storm, all of the HF propagation can completely die off. And what's happening is we're getting so much ionization that the higher frequencies are getting reflected. So we might get good propagation on 6 meters or even 2 meters under rare occasions. But the HF bands, which are normally good, are now getting attenuated by the D layer and become completely useless. Okay, so we've got D layer absorption. What else have we got? Faraday rotation. I need to talk about that. So the ionosphere isn't a smooth surface, but you can imagine it like clouds, clouds of ionized gas. So when the radio wave hits these clouds, it doesn't hit them uniformly. It's not a perfect reflection surface. So what happens is, if you've got something that's, say, vertically polarized, and it starts bouncing around these clouds, getting bent, it's also changing its polarization. So the polarization of the signal that's coming back down is not necessarily the same polarization that it went up. It gets rotated. And that's called Faraday rotation. There's one question on the exam on that. I'll continue on for a bit more. Okay, so propagation, hops and skips. All right, so if you've ever been down to the beach with your children, you've probably done a thing where you bounce rocks off the surface of the sea, you get a nice smooth rock, and you get down low and you throw it in the water and it goes skip, skip, skip. That's pretty much what's happening here with radio waves. The radio signal is going up in the ionosphere, bouncing back, and then bouncing off the earth and going up and down again. So each of these we call a skip. There's actually a minimum distance between the skip. So between where it leaves and where it comes down, there's actually a dead zone here where we can't hear anything. You might hear a little bit of ground wave or direct wave over here, but once we get further out, we've got that path loss, we've got attenuation, we just can't hear anything. The signal that's gone up in the ionosphere gets reflected really well and comes back down to the ground. So somebody over here at C can hear the signal, where somebody over here at B can't hear anything. So I could be operating on HF, and I might be able to talk to somebody down in, I don't know, Ontario, but the guy a couple of kilometres down the road